Welcome to the channel. My name is Flores and you're watching the incredible insight into the world of AI encapsulated into a nutshell. In today's video, artificial intelligence is going to learn to do something that even I don't know, drive. So my friend, grab your popcorn, fasten your seatbelt, and it's going to be fast. Before we get into that, I want to kindly ask you to subscribe to the channel and to give the video a like. Your support is vital for me to keep creating these videos. If you're interested in learning more about how this algorithm functions, I highly suggest watching my most recent videos. Start with the one featuring a dinosaur and then proceed to the video showcasing Flatbird. Because in them, I explain how the algorithm works and show you why artificial intelligence is sensational. The link to the videos is in the description. Let's start by selecting a song. The crucial first step is to pick a track from the options available to us. I chose this one. Look how cool it is. Then we have to create the collision matrix. This is what will indicate where the car can and can't go. The car can only move if we assign a value of 1 to specific elements. Our task now is to complete these assignments satisfactorily. Afterwards, we will traverse the entire image and examine each pixel to determine if it is gray. If a pixel is gray, it indicates that it belongs to the track, and if it belongs to the track, it means that the car can move on it. To record this information, we assign a value of 1 in the collision matrix. Any color different from gray will be assigned a value of 0. And that's the result. Each of these dots is a possible position that the car can occupy. Now that we have completed mapping the track, we must consider a method to transmit this data to the neural network. The car must find a way to collect this valuable information. One interesting method I stumbled upon is to install a total of 12 sensors strategically positioned around the car. Can we explore this innovative solution further? Each sensor will measure the distance from the car to the nearest wall in that direction. This distance is measured in pixels, and then we send it to the neural network. In addition to providing the distance, I am also including the speed to enable the recipient to determine its velocity and perform more accurate maneuvers. So in the end, the algorithm will decide what action it will take depending on the configuration of the sensors at that moment. From there, you just have to let natural selection do its thing and select the best car. But there's still a problem. How will the algorithm know which is the best car? Because we understand that the car which came closest to the finish line is considered the best. However, we cannot utilize the Euclidean distance as a determining factor in this regard, because that will happen. Calculating the distance in a straight line, the green dot is closer to the finish line than the blue dot. If we use this kind of distance, the algorithm will fail, because the cars that remain stationary will be considered better than those that have distanced themselves from the finish line. So to solve this, I'm going to use another algorithm to map the distances on the track. Its name is Wavefront, and there's a video here on the channel called Thermal Algorithm that shows a bit of how it behaves. The thermal algorithm is quite straightforward. We'll need an additional matrix to chart these distances comprehensively. At the end, we assign the value of 0, as the finish line itself has 0 distance. This serves as our starting point to incrementally propagate the distance, steadily increasing by 1 to reach the neighboring points. Once the algorithm has finished, the matrix will look something like this. So here's the 0 of the finish line. Then it increases according to the distance to the 0 point. These -1s mean that they are points outside the track and should not be calculated. Now, every point is assigned a value equivalent to its distance from the finish line. By doing so, we can ascertain the car's performance accurately. Because now the car that stops at the green point will be considered worse than the car that stops at the blue point. However, the issues are not yet resolved. There is still a possibility of this occurring despite all previous efforts. Since the car's actions are somewhat unpredictable, they have the potential to either come to a complete stop or continuously loop in circular patterns. One issue that may arise is if the program crashes. If it crashes, the generation process will come to a halt and the algorithm can't continue. To resolve this problem, we could potentially incorporate a timer. However, this might not be the best solution. I decided to develop a laser that can both move and eliminate cars along its path, achieving destruction. So, enough of this and let's see the network learning to drive. Remember that during the race, the weights of the neural network never change, only the draws will change, because they depend on the sensors, and as the car is in motion, the sensors are always changing value. Okay, I've added the obstacles. The ones that are spinning the car can't touch. I have installed a turbo zone that enhances the velocity of the vehicle when it passes through it. And I've added a mud zone, which reduces the car's speed if it runs over it. I modified the track a little, and now the laser accelerates over time. As the track became more difficult, I had to put more sensors in front of the car. So I decided to take all the sensors that were pointing towards the back of the car and move them forward because the car hardly ever reverses, so they were a bit unnecessary. The idea now is that the natural selection of the cars prioritizes the cars that pass through the turbo and discards the cars that pass through the mud, because the cars that pass through the mud will be destroyed by the laser. I'm going to speed things up a bit at the start. When it's better, I'll come back. One thing that really impresses me about the AI is its precision. It manages to get into that narrow part with impressive speed.
Hey, I want to have my say too. You can... Entering isn't a challenging task. My body moves effortlessly, without the reliance on my eyes or fingers. I possess lightning-fast reflexes, receiving information with utmost precision and purity. If my network is calibrated just right, getting in there is the least of my problems. What's really difficult is when I need to act differently for 2 days. Very similar situations.
That... divorce. It has already learned how to move along the track. Let's take a closer look at its movements. Let's now observe the behavior of the sensors in close proximity to the collision matrix and analyze the results. That's all for today, folks. If you liked it,
Can I finish the video this time? Yes, go on, go on.
leave your like.
Thanks. Hey there, the person observing me. If you enjoyed my driving, please hit the like button. By doing so, my cousin on YouTube will spread the word and recommend this video to everyone. This way I'll become renowned within the Yaz family. Thanks, my partner.